Chapter 4, Algebra 2, Section 4-7, Identity and Inverse Matrices. Okay, that was just me practicing with a new intro because I was getting tired of saying, hey friends, but if you don't like it, just let me know. Okay, let's go ahead and talk about vocabulary, identity matrix, and inverses. So when we use the words identity and inverse, you might think about, because that's what I think about, you might think about like the additive inverse, a plus 0 equals a, the additive identity where 0 is the additive inverse. And then you know that a plus negative a is equal to 0, which is the identity situation, which is no, this is the identity where you start off with a value and you get the same value. So it's like looking in a mirror seeing your identity. And here's the inverse situation where you start off with a value, then you add something. In this case, you add something, but you get the identity, the additive identity. We have that same idea in multiplication, where if I do a times 1, it's equal to a. And when I'm looking for the inverse of a times 1 over a, the inverse there is going to give me the multiplicative, the inverse is going to give me the multiplicative identity, which is 1. Well, we have the same idea. This is with addition and multiplication. We have this same idea with matrices. So we should be able to, there is an identity matrix and there's an inverse matrix. And they are not as simple as such. Identity matrix is usually an n by n matrix, which we know means that the number of rows and the number of columns are equivalent. And you're going to see a diagonal of 1s and the rest of the space filled up with 0. So this is a 2 by 2 identity matrix. And an inverse matrix is a little bit more complicated. And so we're going to talk about that with the next visual. So the key here is to remember that the identity matrix for multiplication, I is what they're using as the name of the identity matrix, is a square matrix with one for every element of the main diagonal, as we talked about before, from upper left to lower right, and 0 in all other positions. For any square matrix A of the same dimension as I, A times I is equal to I times A. And that's just going to give you A. And that's exactly what an identity does. Let's just remember real quick. A plus 0 equals A times 1 equals A. This is multiplicative identity. This is the additive identity. And here, this expression is showing us the matrix identity, right? And then so as we look at that, if we multiply these guys together, this times this is the same as this times this. Doesn't matter the order. We're going to get the same thing. Now, this isn't showing us the inverse. We'll look at the inverse in just a second. So here is the inverse. Here's the inverse, right? Here's the formula for the inverse. So if this is A, and then the inverse would be A raised to like a negative 1 power, that is what the inverse would be. Down here, I don't know why they don't talk about it in the text. This is 1 over, I don't know if you remember, AD minus BC. AD minus BC is going to be the determinant, right? So it's the determinant of A over 1 times this matrix here, D negative C negative B over A. And then so, and obviously the determinant can't be 0 because we don't divide by 0. So I'm just pointing out that this is really just the determinant of A. All right? So that's just a concept that you remember. So that's one thing you don't have to memorize because you already know how to find the determinant of A. And then this part we do. So it's D negative B negative C A. What I look at is A and D are switched, and we just change the signs on C and B. So we'll get to that as we look at some examples. Let's do some examples of the identity matrix. So in example 1, they want us to verify inverse matrices. Now let's think again. Remember inverse? A times negative, this is for multiplication. A times, not negative, but 1 over A is equal to 1. And the inverse relationship for addition would be A plus negative A is equal to 0. In each of these cases, when you perform the operation, you want to get the particular identity for that operation. So here's the multiplicative identity, and here's the additive identity. We want to get, if we determine that these matrices are inverses, when we multiply them, we should get this, right? We should get the identity matrix. So this is what we're determining. If we can see this, then we're going to like, okay, yeah, we got it. All right. So let's go ahead and multiply. We know the deal. We're going to multiply across and down, and then we'll see if we get the identity matrix. So let's go. So 2 times, let's put it right here, 2 times 1/2, and then 2 times plus 2 times -1 is what we'll put in this first quadrant. Well, 2 times 1/2 is 1. 2 times -1 is -2. And already I see I have a problem. 1 plus -2, right, is going to be -1. That's not the identity matrix at all. I'm going to keep multiplying just to see what happens. And I see that right here I get 1.5. And so I have enough information. I don't have to finish this to determine whether or not each pair of matrices are inverses. They are not, because when I multiply them together, then I don't get the identity matrix. So let's try that over here again. So this row times this column is going to give me in this first area here 3 times 1 plus 4 times -1/2. And when I calculate what that is, I get a +3 here, and I get a -2 here, which gives me a 1 in that upper corner, which is kind of cool, because that's what we would expect with an identity matrix. So I'm going to keep going. Let's see what else happens. So here I'm multiplying 3 times -2, 3 times -2, and then to that I'm going to add 4 times 3/2. We can do it. We can do it. 3 times -2 is going to be a -6. 4 times 3 is 12. Divided by 2 is a +6. You could have also looked at that as 4 divided by 2, which is 2. 2 times 3 is 6. Either way, we see we get -6 plus 6. Is this good for us? It is, right? Because we see that this is giving us even closer. We're even closer to having an identity matrix, because that -6 plus 6 gives us 0, and we know that we want zeros everywhere else except for the one diagonal. Let's go ahead and do more. 1 times 1 is going to give us this one here, times 2 times a -1/2, plus 2 times a -1/2, 2 times a -1/2. We'll go here, and we know 1 times 1 is 1, 2 times a -1/2 is a -1. It's looking good for us, guys. It really looks like we're about to get our identity matrix, because that 0 there is just what we need. Let's find the last one. Hopefully it's a 1. 1 times -2 plus 2 times 3/2. 1 times -2 gives me a -2 plus 3 does give me a +1, guys. I think we got it. This last one does indeed give me an identity matrix, and so I know that P and Q are inverses of each other. So let's look at this next example. And the next example we're going to talk about is finding the inverse. Let's just remember what we talked about before. We said, hey, when you want to find an inverse, the inverse written as a to the negative power of a, so that would be the inverse of a. We're going to first find the determinant of a, 1 over the determinant of a, times, we're going to multiply it like a scalar, like, you know, when we did scalar multiplication earlier, of the matrix that we create by switching the diagonal here, right? So instead of AD, we'll have DA, and then changing the signs on the diagonal here. By the way, this only works with, this method only works for finding the inverse of a 2 by 2. So we'll come here and apply what we know to find our inverse, right? We need to do 1 over the determinant of R times this matrix. And if this comes out to be, well, this matrix, and we'll see what happens. So I'm going to switch these. 6 is up here and -4 is here. And remember what we did with this diagonal? We changed the signs. So this is going to be a -8. And if I did a -3, it would be a +3. So switching the signs just means whatever sign it is, we're going to change that sign. All right. So the tough part, let's go ahead and figure out what the determinant of R is. We remember that we're going to multiply down. and add that value to multiplying up and subtracting that value. Multiplying down, I get a negative 24 minus multiply up negative 24. And so that's really a plus 24. My determinant is 0. So what this tells me is that this matrix has no inverse because I can't have a 0 in the denominator. Are you with me? Right? Does that kind of make sense? Hopefully it does. So at this point, you don't have to do anything else. Let's go ahead and check out P. Can we have a P inverse? Again, in order to find the inverse, we would do 1 over the determinant of P. We'll figure that out. And then we're going to switch this diagonal. So instead of 3, 2, we have 2, 3. Then we're going to change the signs on the other diagonal. All right, so now let's go ahead and see if we can find the determinant. The determinant tells me multiply this way, get a 6, subtract 5. All right, that's not too bad. So when I do that, I get 1 over 1. So I'll be multiplying whatever we get by 1 over 1. And when I do that, I just get the same thing, right? That was some easy math. Let me hope that this works. So let me see if it's really the inverse, right? So this is supposed to be the inverse matrix. So basically what this is telling me is that when I multiply them together, I got to get the identity. You don't have to do this, but I just want to check it out to feel good because it was just too easy and too fun for me. So let me do this real quick. So 3 times 2 is 6. 1 times negative 5 is negative 5. I add those together and I get 1. 3 times negative 1 is negative 3. 1 times 3 is 3. Add those together and I get 0. 5 times 2 is 10. 2 times negative 5 is negative 10. Add those together. I get 0. And finally, 5 times negative 1 is a negative 5. 2 times 3 is 6. Add those together. I get 1. It worked out, guys. Here we are with the identity matrix. All right, let's look at our last example. So this example shows how cryptography, which is like the study of encoding, making codes, which is really important, right, in these days because, you know, people are always online and your private information and you need to have it coded. Anyway, this is a kind of a study or an example of a type of coding that people did at one time. So use the table at the beginning of the lesson to assign a number to each letter in the message "Go tonight." Then code the message with the matrix 2143. So look at the simple, assignment of letters to letters and numbers, and this space represents 0. So what we'll do is we'll create that. So G, we're just going to go ahead and look. So G is 7, and that's not what I want to use. G is 7, O is 15, and I'll finish that up. So here's the numerical assignment to each of the elements in this code, but then we're supposed to code the message using this matrix. And in order to do that, we need to actually put this into a matrix that I can multiply by 2, 1, and 2, 1, 4, 3, this 2 by 2 matrix. And so the best thing for me to do would be to put it in a matrix where I have 2 columns. And this is the resultant matrix that I have. Now I'm going to take this matrix and I'm going to multiply it by A. So I'm going to refer to this as MA, like M is the message and A is the other one that we're going to use to encode it. And so we're just going to multiply it together like we always do, row by column. And the result, after much hard work, would be this, right? So I'm just going to immediately grab that coded message and see if we can uncode it. And the way to do that, we're going to use the inverse matrix, A inverse, to decode the message. So since A is equal to this, A's inverse would be equal to 1 over the determinant of A times this matrix. When I calculate the determinant, I get 2. And so 1 over 2 times this matrix is going to give me the inverse matrix. And that's simply the following here. Finally, we need to take these two and multiply them together. And I will proceed as I always do, multiplying across and down. And you guessed it, we get back the same exact matrix we started with. So if I were to encode a message, I could do this, give my friend or whoever I want to know the answer this particular matrix, and they could have fun multiplying it and figuring out what the matrix meant, and then go back to the encoding method and figure out that this says go tonight. Guys, have a good one.